Good morning, guys. Hope you're doing well. So today I want us to talk about friction and drag forces. Now normally when you have an object that's resting on a flat surface, if there's friction between the surface of the object and the object itself, then that idea of friction comes from the natural understanding, or the natural surface, the natural nature, the nature of the surface on which the object is sitting, and the nature of the object itself. Objects might look flat or smooth, but at very, very close inspection at a microscopic level, objects have very many imperfections at their surfaces. So at very close inspection, you'll find these imperfections. But if you look from a far away distance, your eye will assume it to be flat. I'll show you a video of someone who zoomed in so close onto a needle, and at very, very close inspection, even though the needle looks very sharp, it has imperfections. I'll attach that video here just so you can appreciate that idea. So at close inspection, objects have imperfections. Now the object on top is here if it is expanded microscopically, and the object on the bottom is this one that I'm drawing here. When expanded, when you look at it microscopically, what happens is that when these objects are resting on each other, so should have used a different color for the bottom object, but when these objects are resting on each other, what happens is that those imperfections interlock. When those imperfections interlock, in order for you to cause motion of this object, in order for you to cause it to accelerate in a particular direction, you need first to break those interlocking forces. You need to first break these bonds that have been formed due to imperfections. And this is the idea of friction. This is the origin of friction, that force that you need to break the imperfections. Because once you break them for these surfaces, once you're able to break them, then they can slide over each other. When they slide over each other, you have motion. So that's the idea behind friction, is that imperfections need to be broken first before motion can happen. Now, friction for bodies at rest or resting on each other is called static friction. And as you can see, for these objects, or for these two objects on this surface, the heavier this mass is going to be, the heavier this mass is. If this mass is bigger, then the imperfections are going to lock much harder, and then it's going to take you more force to push them. So we can see that force of friction, I'm going to use small f, force of static friction, first of all, is proportional to the mass. But is it only proportional to the mass? Because if it is, if I have this object here on Earth and I take the same object to the moon, what's going to happen? It's going to be easier to push on the moon, but the mass is the same. So I cannot say that it's only proportional to the mass. It's going to be proportional to the weight. It's going to be proportional to the force of gravity of the object. And we know that, sorry, not the force of gravity, it's going to be proportional, forgive me very much here, it's going to be proportional to, if I look at this free body diagram, I have a force of gravity acting downwards, and then a normal force acting upwards. So the normal force acting upwards and the force of gravity acting downwards are equal, but my friction force is proportional to the normal force, not the force of gravity. It's proportional to the normal force Fn acting between these two surfaces. Now to remove this constant of proportionality, I'm going to introduce a symbol. Force of static friction is equal to mu Fn. That symbol is called the coefficient of friction. Mu is so in this case, since this is static friction, this will be the coefficient of static friction. So mu s is coefficient of static friction. Coefficient is basically, if you look at it closely, it's basically the ratio between the friction force and the normal force. Because if I make mu s, it's pronounced mu because it's a Greek letter. If I make mu s the subject, it's going to be equal to the static friction force divided by the normal force. So this ratio cannot be equal to 1, because if this ratio is equal to 1, guess what's going to happen? What do you think will happen? You can, write the answer in the comments. If the ratio is equal to 1, what do you think will happen? If it's less than 1, is that even possible? What will happen? So this ratio of coefficient of static friction is between 0 and 1. Is between 0 and 1. Alright, so that is the coefficient of static friction. Think of an example. If you have a 2 kilogram block resting on a surface of a table, and the coefficient of friction is 0.2. By the way, before we go there, what are the units of the coefficient of friction? Let's see. The coefficient of friction is friction force divided by normal force. Friction force is newtons, normal force is newtons, so the units are, it doesn't have units, it's a dimensionless quantity because it's a ratio of forces. So the coefficient of friction is a unitless quantity. Alright, so we have a coefficient of friction of 0.2, it's sitting on a table. Let's say Hudson wants to move this block, and he applies a force of 55 newtons at an angle of 60 degrees. Is Hudson going to be able to move this block? Let's see. So first of all, if he's going to move the block, then the force that he's using to pull, the applied force minus the friction force, will equal to mass times acceleration. The applied force is acting at an angle 60, so we'll only use the component of the force that's acting horizontally, which will be 5 cosine 60. So I have 5 cosine 60. The friction force, static friction force, is, remember, static friction is mu Fn, coefficient of friction is 0.2, and the normal force is equal to mass times gravity, which is 2 times 9.8, equals the mass, which is 2 times acceleration. So if he's able to move it, we'll have a mass, we'll have an acceleration. If he's not able to move it, we'll not have an acceleration. So if you were to solve for this, and then you find that this force, or that you find that your acceleration is negative, that tells you that the force is not powerful enough to overcome static friction. Okay, the force is not powerful enough to overcome static friction. That's what that would mean. If you find a positive acceleration, that means the force is powerful enough, and therefore there is an acceleration. So that's static friction, and it's friction between surfaces that are resting on each other. Then you have what is called kinetic friction. It's simply friction that exists between surfaces that are rolling or in motion over one another, that are sliding over each other. The formula is the same, the only difference is that kinetic friction is equal to coefficient of kinetic friction, again, times the normal force. Mu of k is coefficient of kinetic friction. And what do you guys think? Do you think coefficient of static friction is bigger than coefficient of kinetic friction, or do you think it's the other way around? You can pause and see what you think. So, thinking about it, static friction, you have more interlockings that need to be broken. But once those are broken, it's going to be easier for the object to move. I'm going to give you an activity that you can do for this and collect some values. So, you'll find that the coefficient of kinetic friction is always less than the coefficient of static friction. That is always the case. So yeah, if you want to calculate coefficient of friction, that's what you're going to use. On an inclined plane, just to look at what that looks like on an inclined plane, because remember, you had your angle theta here, you have an object, this is a free body diagram, it has a normal force going up that way, and then it has a component of gravity, which is Fg cos theta, it has gravity itself, which is Fg, and then it has that component of gravity along the plane, which is Fg sine theta. So on an incline like this, remember the normal force is Fg cos theta, so your friction force, if this object is resting on this incline and there is a friction force F, then that friction force is going to be equal to, the static friction force is going to be equal to Fg sine theta, because that's the equation for the net force. Remember, F net equals ma. Since a is 0, that means the forces acting in opposite directions are equal, so that's why I have F of s equals Fg sine theta. Now we know static friction is mu Fn equals Fg sine theta. Fn, this is capital Fg, Fn is the normal force, and on an incline the normal force is equal to the component of gravity that's acting opposite the surface, opposite perpendicular to the surface. So my equation is going to be mu Fn, which is normal force, which is equal to Fg cos theta, is equal to Fg sine theta. And if you look clearly, the Fg cancels out and I end up with mu cosine theta equals sine theta. If I divide by cosine theta, divide by cosine theta, I end up with coefficient of static friction on an incline is equal to the tan of the angle theta. I hope you'll do some examples on this as well. Okay, so let's talk about drag forces. Drag forces. Now, drag forces are friction forces that exist in fluids. The expression for finding the force of drag that's existing in fluids is, because the drag force existing in a fluid, first of all, is proportional to the coefficient of viscosity of the fluid. Let's call it C. The coefficient of drag is proportional to the coefficient of drag, because different fluids will have different coefficients of drag. Think of it as a coefficient of friction for fluids. The drag force will also be proportional to the area of the object that's falling, because a big area will experience a bigger drag force than a smaller area that's falling. The drag force will also be proportional to the density of the object that's falling. The density of the object, let me use the symbol rho, it's what in physics is used to represent density. And finally, the drag force will be proportional to the terminal velocity of the object that is falling. Density, because even if you have two objects that have the same volume but different densities, you can imagine the picture, they will be affected differently as they fall through the fluid or the air. So to combine all of these equations, all of these ideas, the force of drag is equal to, this is the equation for force of drag. You're not required to show how it comes about at this level, you're just required to know it and to use it, is equal to C, coefficient half coefficient of drag, density, area, V squared. It's proportional, the drag force in a fluid is equal to this. So sometimes you find people writing it as Fd equals B or K V squared, where K is a constant, and that simply means, that's simply standing for the fact that all of these terms for different materials are going, for the same fluid, for the same medium, are going to be constant. The coefficient of drag will be constant, the density of the material will be constant, the area of the material going through the fluid is going to be constant. So the only thing that can change is the velocity in different fluids. But all of these other things will be constant, either for the material or the fluid. So that's why it's summarized into this expression. Now we can do an example. We can imagine that Shuad has gone skydiving and he's falling in head first position, falling downwards, and we want to know the terminal velocity, because the velocity that an object, the constant velocity that an object reaches as it falls through a fluid is called the terminal velocity. So from this expression, Fd is equal to half coefficient of drag, density, area, V squared. If I try to make V the subject, and I'm going to talk about V again, if I try to make V the subject, I'm going to have V squared equals 2 Fd divided by C rho area. So if I take square root, I have 2 Fd divided by C rho area. Now, imagine Sheward falling through a fluid. When Sheward starts falling, the air is going to start acting on him. He's falling downwards with a force due to gravity, but as he continues to fall, the drag force is going to increase and increase and increase until it matches the force of gravity. These arrows should be equal to the force of gravity, until it matches the force of gravity. When it matches the force of gravity, Sheward will stop accelerating. His acceleration will be 0. That means he will be moving at a constant velocity, which is what we call the terminal velocity. So this is an expression we can use to find terminal velocity. If you have the area of Sheward's head, that's if he's falling head first. You have the density of the air. You can find the coefficient of drag of the air, and we know the drag force. As long as we know Sheward's mass, let's say Sheward has a mass of 60 kgs. As long as we know Sheward's mass, we can substitute all of that into this formula. The density of air, I think, is about 1.21 kilogram per meters cubed. The force of drag is right here because it's equal to the force of gravity. The coefficient of drag for air, I think it's around 0.7. All of these values are constant, and there's a table in your textbook. And the surface area of Sheward's head, I'm going to say it's around 0.25 meters squared. So you can use all of those values to find the coefficient of drag for Sheward. The last formula that I want to talk about in this video is called Stokes equation. And this Stokes equation applies the formula we saw earlier for the drag forces. That applies for big objects or noticeable objects falling through fluids. But when it comes to tiny objects, then those tiny objects are best modeled by Stokes formula, which is 6 pi nu, which is the coefficient of viscosity, 6 pi r nu, which is a funny symbol written like that. I want to get it right. Kind of like that, times v. So for very small objects, think of a rat falling through the air, or think of an atom falling through the air, falling through a fluid, even falling through a vacuum. Then for small objects like that, they are best modeled by Stokes formula. Alright, I'm going to give you some questions that you can solve with this work.